Hello, I'm Alan Lind Jensen, and today is October the 1st of 2022. We shall be looking at problem 16. So we have a zeta function being a rational function in t. Meaning it can be written as a fraction of two polynomials. And then we have to show that the numerator and denominator both have the form 1 plus terms with integer coefficients. Of course, we could multiply them by 2, both f and g. So it's that they may be written like this. There are two ways to go about it that I see. One is to get away with all the rational coefficients by multiplying with their least common multiple, both in the numerator and denominator. And the other is to write them with 1, starting with 1. We must use, of course, I'm sure that we are allowed to use that the zeta function lies in 1 plus t set the power series with integer coefficients, which we just proved in problem 15. So that means that the two leading coefficients must be equal. So it can be written with fractional coefficients 1 plus a1t plus a2t squared, where a and b are rational, and 1 plus with b's down here. And then we have to expand and see if we can prove that the a's are integers. It seems like a long way. I prefer to do away with all the denominators, so that we assume that they are polynomials with integer coefficients. And that means that they may start off with anything here, but it must be the same number, of course. So that means we have set of t equals a plus sigma and that must be a as well. All of these being integers. And now we must expand 1 divided by this. And it starts off. Well, that's an interesting guy. How do you do that, really? Or maybe it doesn't become as simple as I hoped. So we go forward till we see the first non-zero coefficient. Oh, this is b divided by a. And then higher terms. This is of course just a. So it's a minus bj t to the j plus higher order terms. So this one comes out nicely. I don't see that will give us any problem. But the higher order terms, there will be a fraction there with a squared. Maybe I should make an example to do it, because I'm not used to have this double series. This is of course a finite polynomial. So let's try to do that correctly. Just leave this. Now, that's something rich. If it's minus, then we'll get plus all the way. But when it's plus, then I think it'll be alternating signs. A little preparation here would have been nice, wouldn't it? Hi, the last 3 days I've been working a little on this problem 16, and not being able to make any progress made me really mad, annoyed. I believe it to be, or believed it to be, a technique problem. So here you can show off your technique. And I believe that I had an okay technique for making such computations. Oh, really didn't like it. Well, in the end, I tried a very simple example. And that makes out an infinite series. Di t to the ith. Etc. And of course, this fraction cannot be simplified, meaning that the series will continue indefinitely. So we will continue having values of d distinct from naught. Now if we multiply with a plus ct on the other side, we get a plus a d1 plus c times t plus a d2 plus c d1 t squared plus a dn plus c dn minus 1 t t to the nth. And this means that the two a's agree as they must. This gives a formula for computing d1, and this must vanish, as must all of these, leading to a dn equals minus c dn minus 1 divided by a. Oh, that was wrong. A minus c dn minus 1, so that dn becomes minus c dn minus 1 divided by a. The point being that we continue to divide by a, and that means that any prime in a will, in a finite step, cancel with the prime power in c, and eventually also take out the prime power of d1. And that means that from a certain point we will have that prime factor in the denominator. So this proves it in the case of two first-order polynomials. And now I guess it's simple to do it in general. So when we come far ahead, we will have a multiplication of these two series, but this only holds, and when I say this only holds a finite number of terms. And if we take the highest term occurring, that's we have to put on up to n, up to m. So the highest term here is t to mth plus some power here. That is cm d, then this we call capital N. Maybe that's not a good idea. Well, let's do that. So that gives, that should give together t to the nth. And that was wrong. It's when we multiply by a, we should get t to the nth. So it's a times dn plus c1 dn minus 1 plus, I'll just take the next one, dn minus 2 plus, and the last one is unity, so that's c n minus m times unity. And that means, now I think you can see how it goes. Actually, I hadn't done this. I only made this example when I started. So now when we isolate dn, we get a sum of products C1, C2, they may actually hold great powers of the prime we've chosen, but one of them will not. So these are the guys I'm concentrating on. So I would like to have the same idea work, that eventually any prime power in A will be eliminated from the D's. And for this we must use some C values. Now let's see the prime. We could of course have a common prime in all of this and not up here. Well, I have made progress and I wanted to report that, but that's about as far as it went. So this is it for today, October the 2nd. Hello. Today, November the 4th, I'll make what is hopefully the last attempt on solving problem 16. But I have given up on it. During October, I spent a little time working on it, and things just got out of hand, and all the things I tried failed. So now I'm reduced to following the hints at the end of the book. So let's see what it says. Write Z. Oops. It must be T, of course. What do they say? 1 plus C1T, etc. And the Q, well, let's do both. P equals and Q with coefficients BI. And of course, now we have extended this fraction so that the coefficients are integers. And of course, A naught equals B naught. Let's just call it, let's leave it. Have no common factors and all coefficients are integers. All right, we'll just write it up. There we go. Check that Q is primitive. That's new to me. Assume to the contrary that some prime P divides all of those. then we have to prove that it also divides all of the coefficients ai. Let's multiply across here. So the constant term is b0 plus, and then we get b1 and c1 b0 plus etc. Oops, that should be n c0 t to the nth. And of course this is equal to a0, this is equal to a1 and an, and it will of course continue, except from a certain point they'll all vanish. And now it's obvious, if p divides all of these factors, then it will divide all of the AIs. I missed that. All right, that was the first point. The next one, use the Euclidean algorithm to what? We know that P and Q have no common factors, otherwise we would have reduced them. So the ideal generated by P and Q in the polynomial ring set with the polynomial ring over the integers contains of all of the polynomials, so it can also get 1. We don't have to actually do the so that's p times u plus q times v equals the constant polynomial. And why is that not? Oh, we're actually doing this over the rational numbers. And that means that in Qx is unique factorization domain. So that's why we can use the algorithm. And that means that when doing this, u and v will have rational coefficients. So we multiply with the minimal number. And then we get an m instead. There we go. All right. And m is non-zero, of course. Right, m divided by q. So we divide this by q. And p divided by q is, what did they call that? Oh, they didn't call it anything. So how should we write it? they introduce new variable for the result of this computation. This is an infinite series, so they are infinite series, all right. And of course di are integers. This is not quite a reduction to 1 divided by q, which was the special example I would be working on. Now, which I not, and neither that could I solve. All right, so m equals, oops, I forgot it, q of t times, times this, guys. So multiplying these, we get m. Yes. It follows by the proof of Gauss's lemma that m divides dj. Let's just call them di. I did, at some point during October, have the idea that, or get the idea that it reminded me somewhat of Gauss's lemma, but I wasn't able to use it at all. And now we still have to work with an infinite series on the right-hand side. Q did not. Q was primitive, so all coefficients of Q cannot be divisible by m. But then if m were 6, then some could be divisible by 2 and others by 3. So maybe it wasn't necessary that all of these were divisible by dj. All of these were divisible by m. I'm thinking about taking 1 prime in P and then working on the localization of Q with respect to that, and in that ring use Q will be primitive. I've never worked with those before, so I don't know if that's an idea. how about taking the first di that does not divide, that m does not divide? And then let's use the first, consider the first term where dk, then we take -1, where dk enters. We just have to look at the constant term first. Q of t, that was a naught times d naught Now let's look at this guy. The constant term are a naught in both of these, so m must divide a naught on the opposite. No, m must be a factor of a multiple of a naught. So it follows up here that a naught divides m. I have no idea what he means. So we should use the proof of Gauss's lemma. But this is an infinite series. Q is primitive. I'm confused here. I believe it's time for a little break. I will take my bicycle and go to the bakery, buy some cakes, make a cup of coffee, and then I hope that I understand what I'm supposed to do here. I have had my coffee, and some time has passed. It's now 2:30, or rather 20 to 15. I'm changed these to B's. I made a mistake. That's corrected now. I looked at this again with new eyes, and it seems that we have to prove a proposition like Gauss's lemma, and I think this is the one. So if we have two polynomials, f being a polynomial and g an infinite series, and both are primitive, then the series f times g is primitive. So that's the proposition. And we try to mimic the proof of Gauss's lemma. So we write them f equals sigma ai x to ith and they are both primitive. So that means that we have a j. So take some prime. Choose prime. Or that is, if it's a uniform factorization, then it's irreducible. I don't know if irreducible is the same of pri in a UFD, really. That means that we have some that p doesn't divide, and so we choose a naught to be the smallest. So p divides a naught up to a, what did we call it? We can call it j minus 1, and p divides j, doesn't divide. And the same with b, we call that k, fails to divide, b naught up to b, I just made it again, k minus 1, where p divides b k. And something should happen when we take j plus k. So coefficient to x j plus k, a naught b j plus k, and then we get somewhere in between this guy oh, that was not what we should have. Now where does that happen? It's actually yeah, that somewhere in the middle. I'll just take the next one. This is B's, of course. So a naught to a j minus 1, p divide those, and the b's here are divided by p, whereas p fails to divide this guy, and then this residue modulo p cannot vanish from the coefficient here. Now I just miss what I'm doing here. I want to show that any prime will have some term in the product that it doesn't divide. provided both f and g are primitive. And that's what I've found here. All right. You see, this point I missed the whole month because I was looking at the case where instead of m we had unity here. I simply considered 1 divided by q and never thought of using Gauss's lemma because it was an infinite series, so no, it doesn't work. All rightio. That means that this is not needed. So we should prove that m divides. Now, what do we have? We have now what do we have? We have q is primitive. And then, now, did I prove that d was primitive? Or rather, if this series is primitive, then m is primitive. Meaning m equals plus minus 1. I just lost it again. I thought I had solved it by now. Now I can see it from a proper distance. If this series fails to be primitive, we can take out a factor, say p. Then this product will be m divided by p. Now, then this product will be primitive, means it's unity. So all the factors we can take out. Oh, that shows exactly what I needed. If it's primitive, then m is plus minus 1, so m must divide each of them. Particularly, that's the next point, it must divide d naught. And d naught, that's, what's that? What does that mean, really? Now, I need a hint even here. This means that the constant term b naught is a unit. If m divides d naught or B naught, this means that B naught vanishes. B naught divides M, M divides D naught. We need to go back here. I believe I'm missing something very, very trivial here. But I'm still thinking in complexities, like if we have to multiply, to multiply these with the same, so we get the same here. So we have the same constant factor. So m is a multiplum of this. Oh. Now, if we have this, and then, oh my God, that was really poor. We have m equals b naught, d naught, unity equals bn times d naught divided by m. If this is an integer, then b is the inverse of this integer, primitive. So that means b equals unity. All right. And that means that when we extend p and q, we end up with having to do nothing, and that means that the original coefficients are integers. Now, this is the proof of Gauss's lemma that came back to haunt me. When I studied, I think I was tired the night I read it and thought, yeah, that seems right, instead of checking the details of it, so I didn't really internalize it. And had I done that, it would probably have been rather easy for me to recognize that it could be extended to be a polynomial with a series, or actually two series. Interesting.